Hello. Hello. Good evening,
Hello.
Nilanjan. Sir has joined. Hello. Am I audible?
Yes, ma'am. Can we start? Hello?
Wait. Just
Yes,
we
ma'am.
will wait till 6. We will start at 6.
Okay, ma'am.
Okay, ma'am.
Nilanjan, sir? Good evening, Nilanjan, sir. Swati, madam, we can start the session. Sir is ready.
Okay, ma'am. Good evening, everyone. I'm Dr. Swati Kale, the session coordinator for this session. It's my absolute pleasure to welcome you all to this highly anticipated session of our faculty development program. Today, we are privileged to have with us a distinguished expert in the field of artificial intelligence and medical imaging. Allow me to introduce our esteemed speaker, Dr. Nilanjan Day, a senior member of IEEE and an accomplished academician and researcher. Dr. Day completed his BTech and MTech in Information Technology from the West Bengal Board of Technical University and earned his PhD in Electronics and Telecommunication Engineering from Jadpur University, Kolkata. With a remarkable academic journey spanning over a decade, he has made significant contribution to the field of medical imaging and machine learning. Currently, Dr. Day serves as an associate professor at Techno International, New Town, Kolkata, and he is also visiting fellow at the University of Reading, UK. His research portfolio is truly impressive, with over 300 research articles published in peer-reviewed journals and international conferences, along with 40 authored books. Dr. Day is deeply involved in the global academic and research community. In addition to his research and academic endeavors, Dr. Day holds several editorial leadership roles. He is the editor-in-chief of the International Journal of Ambient Computing and Intelligence and associate editor of IEEE Transactions on Technology and Society, and served as a series co-editor for Springer and elsewhere publications. Today, Dr. D will share his insights on AI-empowered medical imaging opportunities and challenges. Without further ado, please join me in giving a warm welcome to our expert, Dr. Nilanjan Day. Over to you, sir. Thank you. Hello, Day, sir. Hello.
Yes, ma'am.
Hello.
You're audible.
Okay.
But sir's voice is not coming, right?
Yes, ma'am.
I will communicate to him. Just a minute. Because let's see, he might be checking his connection. Hello, sir. Nestor, sir.
Ma'am?
Nestor, sir.
Yes,
Please
ma'am.
unmute, sir. Sir is muted.
No, ma'am. I have already given co-host access. So, ma'am, sir
Once
can unmute
check
himself.
it. Check it. Sir has given me the message.
Sir, are
Check
there
it.
two screens?
I maybe possibility. There is a possibility.
No, there is only
Need to
one,
ask.
ma'am. I have given co-host. Same
You check
access.
for whether there are multiple logins and then you can understand. I'll ask sir whether you have done
Multiple
that particular.
logins.
Yeah, multiple login है क्या पूछते हैं because he is asking to unmute.
Ma'am, actually, according to his name, he is already unmute. Only video
Okay.
is close.
Given the access, video is
Already.
also keep it on, no? No
No,
problem.
actually,
नेस्टर
sir
सर
has the access.
नेस्टर सर कॉल करके पूछ लो एक बार which login they
Sir,
are using.
I am doing the communication. No problem. I'll call him.
हाँ, so the problem, please.
He is asking for waiting for a minute. We'll wait for.
Okay, okay.
Yeah. Yes, day sir. You're visible, but voice is not coming. Nestor sir. Nestor sir.
Yes, ma'am.
See that sir will log in again.
Yes, ma'am.
Yeah.
Hello.
Yes, sir.
Yeah, sorry, maybe some technical issue.
Yes, sir.
Yeah, please.
Yes, sir. Please start, sir.
Okay,
Yes.
so it's audible and visible, right?
Yes, sir.
Okay, thank you.
Thank you, sir.
So next 1.5 hours, 1.5 hours, talk about how AI actually changes the whole medical imaging. As a paradigm shift, you can say. What are the different opportunities and what are the different challenges? So let's start with some statistics. In India, per patient, uh, I mean, how much a doctor used to spend time, and per doctor, how many populations they used to cover. And the number doctor to patient ratio is 1:8,434. That is a number you can imagine that there are 834 population, which is covered by one single doctor. And amongst those doctors, there are almost 5.6 lakhs doctors are ASUS doctors, means Ayurveda, Yoga, etc., etc. So that is a number. And per patient, in states, a doctor used to spend 21 minutes. And in India, per patient, a doctor used to spend on an average 2.3 minutes. And in Bangladesh, 48 seconds. So you can imagine that 2.5 minutes is, mostly not enough time for a doctor to decide what type of disease you are having and the diagnostic procedure and then the medication. So this number actually motivates to work with, CAD system development. And the last one, as doctors are human being and there is a very less number of time, so that's why medical errors comes into the picture. And this number is something 5.2 million per year in India. So medical errors are very common because of this crunch of time and the coverage of the patient or the population by a particular doctors. Now, once we talk about these medical errors, we are not actually considered the medical negligence, because negligence number might be huge. But once we talk about medical errors, typically there are three different types of error. One is the medication error, means incorrect dose, inappropriate medications, etc. Second category is the surgical errors, which is a kind of operational kind of errors. And the third one, which is a major category, that is the diagnostic errors. So once they try to interpret the test or the imagining, there might be the imaging part comes with a, say, wrong diagnosis or incorrect treatment planning. So that's why the main motivation of doing medical imaging, deploying CAD system, or you can say it's a computer aided diagnostic system. The basic motivation is to give the doctors a second opinion so that the doctor can come up with a faster decision and accurate decision, just to reduce the number of this error. So that's why once we talk about computer aided system, the doctors having the qualitative knowledge. So that qualitative knowledge can change into a quantitative paradigm. So to make this into a quantitative paradigm, we need to go through or pass through the image analysis technique, especially radiological images. And then after that, we used to deploy the, AI, you can say intervention of AI. But typically, once we talk about these CAD system, it's a kind of second opinion to the radiologist. So that it can come up with a faster, as I said, and it's a kind of correct decision-making process. Now, sorry. So once we talk about CAD system or computer-aided diagnostic system, typically there are three different categories. The first category is called the computer-aided detection. That is a CAD-E category. Second category is the computer-aided diagnosis. That is the CAD-X category. And third category is the quantification. So CAD-E, CAD-X, and CAD-Q. So those who are working in detection, they might not work into diagnostic. Or ones who are working on diagnosis, they might not work into the quantification, because these are three different types of software. So one of software, they used to detect the location of potential calcium. Maybe there is a cancer growth, or maybe calcium is growing somewhere, something like that. So it's called a CAD-E category. They try to detect, or they try to localize, means this is a particular location where the potential cancer or the calcium is growing. And once we talk about CAD-X category, that talk about the likelihood. Means suppose there is a lesion, the lesion is the benign or it's a malignancy is there. So the presence of the disease, that particular malignancy, we used to detect by that. So that is a diagnostic one. And third category, suppose there is a tumor or maybe a wound or bulge or lesion. So they try to quantify what is the size and what is the shape of that. So these are the three different types of software. One type of software is for the detection mechanism, one type of software is for the diagnosis mechanism, and one type of software we used to deal with the quantification. And these typically three different types of CAD comes under one particular umbrella, that is which is called a whole CAD system or clinical decision support system, which is you can say is a kind of helper or is a kind of second opinion provided to the radiologist. So that's why once we talk about medical imaging, basically we talk about CAD system designing. So computer-aided diagnostic system designing. So it might be for the detection, might be for the diagnosis, might be for the quantification. Now, if you look into the medical image, you will see the entire different modalities. If you consider from CT images, mammogram, say intravascular ultrasound imaging, or UV image, maybe radiological image, almost 75 to 76% of the overall medical imaging are radiological images. But apart from these, there might be, say, endoscopy, there might be retinography, what is called the ophthalmo images, or maybe the derma-related images are there. There also CAD can be deployed, but less. Majority of the CAD actually deploy this 75% to 76% modality, which is called the so-called radiological images. And once we talk about these radiological images, what it actually do, it try to give a kind of pattern recognition problem formulation. Now, how it actually works. Say, for example, as I said, it's a kind of typically or highly complex pattern recognition system. Say, for example, you have an X-ray and there is something hairline crack, so, or maybe some suspicious structure. So we need a lot of X-ray data. And then from there, we try to come up with an optimized framework. And then we try to analyze the pattern, what type of, say, the suspicious structure is there present or not. So it's a kind of, typically, you can say it's a CAD system is nothing but a highly complex pattern recognition problem statement. Now, for that, we need a CAD server where we used to deploy or put a lot of DICOM data. And DICOM data means it's a kind of so-called high-quality medical data. But in general, in India or in Asian countries, you will see that the data or the radiological data are already compromised data, low-quality data, perturbated data, noisy data. It's a kind of sometimes QTV data, compressed data. So we generally not get DICOM data. But if you get DICOM data, you are lucky enough because you have good quality data, which is good for image analysis. But if you don't have DICOM data or so-called high quality data, it's sometimes very difficult or a huge task for people to identify the potential disease and go for the diagnostic mechanism. So that's why we need a lot of data needs to be stored into the CAD system. So now, once we talk about medical imaging or this radiological image, as I said, the images are already compromised and perturbated data, noisy data. So the basic step, the first step need to be go through a pre-processing phases where you need to remove the noise. Maybe you go for the filtering process, maybe you go for the labeling, or there can be different types of artifacts are there. And then once you improve the quality of the image a little bit, maybe you can go for the segmentation. So once we talk about the segmentation procedure, there is a kind of foreground and the background separation. We try to identify what is the region of interest. Then identifying the region of interest, the non-region of interest might be into the suppressive mode. And then we analyze that particular region of interest zone, which is called maybe the compaction, maybe the size or the localization we used to identify. Sometimes it might be 3D visualization part, maybe colorization technique, etc., etc. Then after that, we pass through some traditional machine learning mechanism. We try to extract the features, put it into some classifiers. We used to get some accuracy. So if you look into the CAD system, there is a kind of visualization part. There is a kind of, say, segmentation and quantification part. There is a, say, recognition of the modeling design part. And one part is a decision-making part. So this is whole actually how the CAD system works. Now, talking about this image database, they used to go for the pre-processing, extraction of region of interest, feature selection mechanism, put into the classifier, getting some predicted result. And if it's a satisfactory result, the diagnostic result passed through. So this was the earlier cases. Before 2014, people used to do this kind of shallow machine learning mechanism. But after 2014, once DeepNet first, say, AlexNet introduced, there is a huge change in the whole medical imaging paradigm. You can say it's a paradigm shift in 2012 to 14, that time, where the first time the shallow machine learning, it's moved to another paradigm of deep learning framework. But we try to focus on traditional machine learning techniques, the so-called the shallow machine learning techniques. We try to understand what are the different challenges, why actually it need to go through the shallow machine learning to the deep framework, and what are the obstacles and how can we overcome those obstacles. Once you go for the shallow machine learning process, then we will move to the deep learning framework. Now, let's start from the segmentation technique. So segmentation, as you all know, we try to divide the image into similar property based on the similar property, maybe the gray level, maybe the texture, maybe the color, brightness, contrast level, etc., etc. By talking about the challenges, see, in traditional machine learning, any kind of image segmentation technique, once you pass, you might not face such kind of problems always. These are some typical issues which you will actually face once you go through the imaging technique, which is related to medical imaging. Now, the first example, let me give you one example of a particular disease, which is called atherosclerosis, which is a very common disease after, say, 60 age group. So people suffer by, say, atherosclerosis disease. What is that disease? The disease is something, the calcium is deposited inside the artery or artery wall, or it may be sometime in coronary, it may be in the carotid. Now, what happened inside the artery wall, the calcium is getting deposited, and calcium is not deposited in a single place. Inside the artery wall, the calcium deposited in a many small chunk all along the path of the inside the artery wall. Now, what happened once the blood is flowing through the coronary or maybe the carotid, it goes to the brain. Suddenly, the calcium touch each other wall, and there will be no blood flow, and it's a kind of cerebral attack. Now, what happened? This particular technique, imaging technique, is called the intravascular ultrasound imaging. You will simply put a probe, or you can say it's called a catheter. You put the probe inside the artery, and now you rotate that probe. It will emit the sound wave. The sound wave will refract from the inner wall of the artery. Where there is a calcium, the refractive index. Where there is no calcium, the refractive index will be different. Based on that, we try to find out where exactly the calcium is deposited and how much calcium is getting deposited. So based on that, we assess the stroke risk. Now, what happened? The first thing is the potential, the volume effect. Means sometimes the calcium is not depositing, as I said, in a single place, because the disease, atherosclerosis, is a multifocal disease. So there are a lot of different phases, lot of different places the calcium is getting deposited. So if it is amalgamated in a single place, it's easy to segment. But if there are a lot of small chunk, it's very difficult to segment, because one place, the whole amalgamation, and different places, small amalgamation. So these are typical problem for this kind of intravascular ultrasound processing. Now, second is, once you put the probe and rotating, that means inside the artery, that might the probe having some shadow. So within that shadow region, if some calcium lies, you fail to detect, or your any segmentation method will fail to detect. Let me give an example. If there are 3 buses, and beside the bus, there are 2 bicycles. Now, if there is an UAV which is capturing how many numbers of vehicles are there, Now it easily can capture the 3 buses and 2, the cycle might not be actually detected by UAV. What happened? The bus might have shadow. In that particular shadow region, if the 2 bicycles are there, it might not be able to detect because of the shadowing effects. So for that, what we need to remove the shadow. So you need to pass through some shadow removal algorithm, which will remove the shadow. Then only it can identify, okay, there are 5 different vehicles are there. So same thing happens also here. Like if you put a probe or catheter, the catheter might have shadow. Within that shadow region might some calcium deposited. So you need to first pass through a shadow removal technique. Now intensity inhomogeneity. So the intensity of the pixel value, it's not homogeneous in nature. So that can be another problem. And there are a lot of artifacts during the imaging technique. Once you're trying to acquire the medical image, there can be a lot of artifacts present. As I mentioned, that the noise is a very common thing, perturbation is a very common thing. So this comes into the picture. And lastly, once we deal with the radiological images, the value range of the gray value, pixel value, are very close to each other, maybe in the darker side. So the closeness of the gray level of the different soft tissue is also a big challenge. So these are typically some of the problem which you actually face for image segmentation, medical image segmentation. One is a partial volume effect, one is a shadowing effect, might be the inhomogeneity of the intensity value, or the presence of the artifacts, or the closeness of the gray value of different soft tissues, etc., etc. These are the few of the limitations. But apart from these, there are a lot of other segmentation obstacles are there. Now, if you think any segmentation algorithm, you will see typically there are 3 different categories of segmentation. One category based on the gray value. So suppose if you have one particular image and you are trying to plot all the gray value into a histogram, and you are trying to find out 2 values, say T1 and T2, and you are trying to split the image into 3 different, say, gray value, say 0 to 55 substituted by 40, 55 to 200 substituted by, say, 65, or 200 onwards, all will be substituted by 210, something like that. So you go for the content analysis, or you are trying to find out the region of interest. Now, the biggest problem is to identify the T1 and T2 value, the threshold value, because this threshold value can change based on the patient, based on the modality, based on the alignment of the patient, based on any acquisition system. So for a particular modality, the T1, T2 value is not a fixed value. So manually, if you try to detect this T1, T2, based on which you are trying to do the segmentation, histogram-based segmentation, you will see ultimately it will be a failure case. And if you go for the adaptive technique also, then also you will see the same type of problem will recur. So that's why histogram-based any segmentation strategy, there are n number of strategies are there, are generally failed because of one reason, the selection of T1, T2 value. For T1, T2 value selection, this is a good example. Professor Pass in 1997, they come up these 2 images and they reported these 2 images are exactly same. Again, I'm repeating, these two images are exactly same. If you study the histogram, color histogram, RGB, you will see the histogram of these 2 images are exactly same. But apparently, even though they are same, but you will see these 2 images are completely looks different. But histogram are same, similar color histogram. So that's why it's quite difficult for many of the cases. If you set the histogram, based on the histogram, if you try to do the segmentation, it might be a failure case, because you are only looking into the histogram and you are trying to categorize the region of interest and non-region of interest. So this is one example where the T1 and T2 plays a significant role, even if it is a manual or it's an automated. All the segmentation strategy based on the histogram are somehow struck here. Now, here also the T1, T2 selection can be carried out by different techniques. It's a completely open research area where people try to identify what will be the exact T1, T2 for MR image, for CT image, for any other radiological images. But still now, the adaptive techniques, many of the cases not works fine. Second category is the age-based segmentation. You will see another M number of algorithms are there based on age-based segmentation strategy. So that it try to identify the ages, or you can say the contours, And based on the contour selection, they are trying to segment the image. This is the foreground, this is the background. Now, the problem is once you deal with radiological images, as I mentioned, the main thing is the presence of the noise. So if the noise is there, and once you go through or pass through any age-based segmentation strategy, it might identify a particular part, which is a kind of age. But ultimately, you will see it's not actually age, it's a noise detected age. So which is called a false age. The presence of the noise makes false age generation. Even you identify this is an age, but that age is nothing but a false age. So that's why we need to come up with some filtering strategy, which actually, once you pass the pre-processing techniques, it will never actually smoothen the age information. What I'm saying is, there, say, for example, you are deploying one filter and it actually smoothen the images. So it's remove the noise a little bit, and the age information is getting continuously losing its information. Now, what will happen once you go for any age-based segmentation, the age detection is already compromised. So that's why you need to come up with some filtering strategy which will preserve the ages. So that means the filter will work everywhere except the ages. So if there is an age, the filter will stop working. And once there is a non-age, that means there is no change of dy/dx, flatten, the filter will work. So age preserving filter design is another problem statement. Many people actually work to come up with a filter design where it will retain the age information so that the diagnostic value of the ages will not get affected. So that's why these are the limitation of age-based segmentation. And you will see, as I said, there are m number of algorithms are there. So many algorithms are there which are based on age-based segmentation strategy. And the third and the last category is the region-based segmentation. In this particular technique, what you have to do, you have to identify some certain points. Those points are called the seed points. Now, those seed points will grow, gradually grow. So based on the gray value, it will try to merge. So if the gray value are similar, it will try to merge. So it's a kind of region merging technique. Or it might be there is a large area and you are trying to split it into small pieces, rather small pixel chunk based on the gray value, similar value. It's a kind of region splitting. So either kind of merging or it might be a splitting kind of technique. So it's a region based segmentation strategy. Now what happened if you go for region based segmentation? It's a very common problem is under segmentation or over segmentation. If there is an under segmentation, the medicine might not work. If it's an over segmentation, if you're dealing with a brain image, you are doing something, say over segmentation, region segmentation based analysis, you will see the medicine which you actually deploy, giving to the patient might get a stroke. It might happen. So that's why under segmentation and over segmentation is a very common problem for region based segmentation, because where to stop is a big problem. How many numbers of small pieces or chunk you require, there is no hard and fast rule. So optimal selection criteria for this segmentation strategy is itself a big problem. There are many heuristic strategy, meta heuristic strategy people deployed. Like say, for example, deploying say PSO, maybe genetic algorithm, DE, etc., etc. People deployed and tried to find out the optimal number of segmentation value. So what will be the number of the segmentation? But ultimately, these are something which not works, or sometimes it works for some cases, but majority of the cases it's not work. So as I was trying to mention that image segmentation technique for medical imaging, which are in general three category. One is the histogram based, one is the age based segmentation technique, and last one is the region based segmentation technique. And all these three segmentation technique, different techniques, under which any of the segmentation comes, almost every segmentation comes under these three category, having their own limitation. So that's why what people try to do, they try to combine. So they try to combine the region based with age based, or age based with histogram based, some hybrid technique. And again, this hybrid strategy might sometime work, might not sometime work. Again, it's a very challenging task to actually identify that which particular segmentation strategy will work. So what I try to mention, The very first thing is the pre-processing. Pre-processing having a lot of hurdles, which I will discuss. But the second thing is the image segmentation technique. Until you segment your image properly, you can't identify the region of interest. And if you fail to identify the region of interest, the whole machine learning model, which is based on the region of interest selection, that will be a failure case. So that's why segmentation is the fundamental, problem statement for any medical imaging. You have to correctly identify the region of interest. And all these segmentation strategy having their own limitation. And this even the hybrid also. Now, this is one example, which is a kind of, you can say, there is a lesion. You are trying to detect the what is the shape and the size of the lesion. So now you are trying to fit a curve, elliptical parametric curve, and the curve will try to fit in such a way wherever the energy is getting minimum, it try to catch that. If the image is small, if the number of iteration is small, it might works in many of the cases. So it's a contour-based model. You can say it's a kind of, as it is detected the contour, or it's a kind of region merging also. So is it a region merging or is it a kind of contour? So this is another question. So it's a kind of region-based segmentation. It's capturing the age information, but it's a global region-based segmentation. This is one segmentation strategy, which is a very old technique, which is called the contour-based model. There are a lot of variant of this particular algorithm, like say, for example, snake model is an example. If you search with snake model, you will see many people actually deploy this contour-based segmentation strategy if the image size is small and the image is of good quality. So this is one example how the region-based segmentation works and to capture the age information. It's a good strategy again. Now, once you have this segmentation result, then the next part is you need a ground truth. Ground truth means the doctor will draw the ground truth or the hand, say you can say the benchmark data for you. So say for example, the ground truth here, the green might be given, the blue might be given by your computer diagnostic system, which is your segmentation result, and the red might be given by the doctors. Maybe one particular doctor you can consider, or you can consider multiple doctors, and then you come up with an averaging. So if you have trust on a particular doctor, you get one benchmark. If you have many doctors help, support, you can come up with multiple doctors hand trace, and you take an average. Now what you will do, you will try to compare the blue line with the red line. So which is called the figure of merit or precision of merit. So you are trying to compare what is the variability. How close your segmentation result is with the manual detected ages. Now, if they're very close, or it might be the variability is very high. So based on that, you will try to find out how good your segmentation strategy is. Now, figure of merit or precision of merit actually gives you a value which tells you how good your segmentation strategy is. Sometimes it might be inter-observer within the observer, or intra-observer between two different observers, the variability. You are trying to find out how good it is. So amongst one doctor's two hand trace, or multiple doctors, multiple hand trace, you are trying to fuse, you are trying to get a mean value, and you are comparing with the result, and you are finding out, okay, this is my system's the segmentation accuracy, how precise it is. So you are trying to identify those F measures and all value. So this will actually give you a kind of result analysis by which you understand, okay, this particular segmentation is working because precision of merit is very high, or the figure of merit is very high. So as I said, there are thousands of segmentation algorithms are there. It's very difficult to identify for which particular modality, which particular segmentation will work, and how good the segmentation will be for a generic cases. So this is an open challenging problem. Segmentation itself an open challenging problem. Now, what happened exactly once you segment? Say, for example, there is a disease called the glaucoma, which is a very well-known disease. Glaucoma is a second leading ophthalmo disease. First is a cataract, second is the glaucoma. So almost 1/3 of the patient of cataract is actually infected by glaucoma. Now, you will see the majority of the people work in glaucoma, not in, say, cataract. The reason is cataract is an operation of very few minutes, but the glaucoma is a kind of silent killer. So it's simply, there is no symptom, it's simply, you will see the vision is getting lesser and lesser. So what we try to do, we try to find out the ophthalmic cup, optical cup and the optical disc. So this is your optical cup and this one is your disc. Now this optical cup to disc ratio, if it is above 0.58, it's a clear case of glaucoma. So we always say there should be a real-time mechanism. Sometimes it's kind of mobile app kind of. You can assess, okay, what is the optical cup and what is the optical disc and what is their ratio. And if the ratio cross the boundary of 0.58, there is a case, it's a kind of glaucoma case. So now to identify the optical cup and the optical disc is itself a kind of open challenging problem. Many people used to work on glaucoma. They try to identify the cup and the disc properly. So once you do this, say for example, this is one example, because of the brightness and the contrast level of the image, the segmentation strategy might not be able to capture the optical disc or the optical cup properly in many of the cases. Say for example, 100 cases are there. Say 4 cases or 5 cases, you will see the algorithm is not working. So for those cases, to improve your machine learning model's accuracy, or you can say it's a more generic result if you want to get. So you need to rectify those 4 guys, which are so-called bad guys. So for that, you need to give the doctors a platform, which is called a post-processing platform, where the doctors can hand tune. They can change those pointers. They can manually set those points. They can freeze it. So what I'm saying is the automated system give you an outline. Many of the cases it is correct, but some cases it might not work properly. That time the doctor's intervention required. The human intervention will make the whole process more robust. So sometimes semi-automated segmentation is a very important category of segmentation for imaging, medical imaging, where the human intervention is required. It's a so-called post-processing technique. Because I mean, automation is always good, but once we talk about medical imaging, human intervention sometimes makes the system more, acceptable system. This is one example. So as of now, I was talking about the second part, which is called the so-called segmentation strategy. Now then comes the color, the feature one. So feature analysis, as we are talking about the shallow machine learning strategy. So you have to identify the features from the region of interest. So you segment properly. Now the feature comes into our mind is a color feature. Now say for example, you are dealing with the diabetic retinopathy. So there might be soft exudate, hard exudate, macrocalcification. It can be hemorrhage, it can be duration, etc. So the shape and the size, the roughness, the type, the depth, the color, for all different cases, you will see different. Sometimes it's a cotton-like structure, sometimes yellowish, or sometimes whitish, etc. So color can be a prominent feature for many of the cases. But unfortunately, once we deal with radiological images, so-called radiological images are non-color. If you are dealing with say retinal images, if you are lucky enough, you have the color feature. But many of the cases, color feature not work properly. So that's why the second category of the feature is a texture feature. Say for example, you have a microscopic image. This is a kind of say mice image, and there are say haptic mice image. There are a lot of cancer growth, different level of cancer growth is there, fibrosis. Now you are trying to chunk into small pieces. These are all say you can say intermingled points. Now from there, if you look into these 3 categories, you will see that texture is prominently different. So it's a kind of, this texture will tell you that these are the fibrosis, what level it is belonging. It's a 1 or 2, what level. So these are the categorization of the fibrosis. Or you can get an example from the breast cancer classification. So if there is a fat or fat granular or dense granular, so color is a prominent feature for this. Apart from this, texture can also be a good feature. So you can analyze what will be the texture of the fat or the fat granular or the dense granular, and based on that, you can find out, okay, the chances of the breast cancer is such and such. So this texture is the second feature. And the third feature is a shape-based feature. Say, for example, there is a periodontal ligament inflammation. So it's inflamed, and you don't know what geometric shape it is, because it's not a proper geometric shape. Now, what we'll do, if you want to train the shape to a machine learning model, it's very difficult to, train a non-geometric shape. If the shape is circle or square, rectangle, it's easy to say map, or you can easy to train. But if it's a non-geometric shape, we try to put an elliptical curve. Now, this is your elliptical curve. You are trying to fit in an ellipse, and you are trying to identify, okay, this is the deformation and how much getting deformed. So a non-geometric shape, how much getting deformed from a proper geometric shape, that deformation need to train to a model. That deformation training is called the shape feature training. So these are the three typical categories of, say, features. One is the color feature, one is the texture feature, one is the shape feature. If you talk about, say, heraldic features, or say, you can say the grabber feature, any feature selection, any feature selection algorithm, you will see ultimately they might mostly come up under these three particular feature category. Now, you have a lot of features. So if you have n number of features you collected from by analyzing the image, color feature, texture feature, shape feature, etc. So this large number of feature you are actually incorporating into a machine learning model. Now, what happened if the number of feature is too high and the data set is less? Say, for example, you have only 100 X-ray images and you are trying to find out, you are trying to train your system, and there is so many numbers of parameters or so many numbers of so-called features are there. Now, what will happen? The large variance estimation. So you will see there is a large variance. You will see the machine is getting overfitted, because overfitting is very common because the data set is very less. And the training will be expensive because there are too many numbers of parameters, too many numbers of features. And the presence of duplicate feature, poor predictor is very common. So that's why you need to pass through a proper ranking strategy. And that ranking strategy will identify, okay, this feature you will incorporate, this feature you will not incorporate based on some statistical measure. Maybe some correlation strategy, say ANOVA, chi-square, etc. You are trying to identify, okay, these two features are close enough, I will exclude one, or these two features are not close enough, so I can incorporate both the features. So in this way, you need to pass through a proper selection strategy. So feature selection strategy you need to deploy, then you come up with some certain number of features. So as I mentioned, there are two different strategies. One is filtering method, one is called the wrapping method. There is another third strategy also, hybrid technique. So filtering method, if it is the feature is a response is continuous and the response is also continuous, so maybe Pearson, or maybe sometime continuous categorical, it's an LDA, categorical continuous, ANOVA, categorical, chi-square. So the basic notion is you are trying to find out how close the features with each other. And wrapping is a separate, exactly opposite. One is the inclusion strategy, one is the exclusion strategy, exactly the reverse strategy. And if you combine these two, it will be a hybrid technique. This selection mechanism is a very common technique, and majority of the people know that how to come up with a feature selection strategy. Now, once you end up this, now think what we did until 2014 to 15, that time. People once did this shallow machine learning technique. The challenges was starting from the pre-processing, the selection of proper segmentation strategy, and the different challenges of segmentation. Then after that, which particular feature you will select, which particular feature selection strategy will be there. So there are so many numbers of different phases where the manual intervention required. And the system, the whole CAD model is very much biased towards the selection strategy. What type of mechanism you are selecting, based on that machine learning model gives you a result. And that was the biggest challenge. Because each and every step, if it's actually depends upon the human intervention, and if the processing having lot of, say, interdependency and manual intervention is there, so ultimately the system can't be a robust system. So there was actually a need to pass through all these processes by some mechanism. There should not be any kind of, say, so-called, increasing the quality of the images. There should not be any kind of strategic planning required for segmentation. There need not to be any kind of feature selection strategy, feature reduction strategy. You need not to pass through any. So there should not be, you need to pass through, they say PCA or LDA, something like that. It will select a particular set of features. No need to do this. So that was the basic motivation to design the CAD system, and the CAD should be a deep learning based CAD, which is so-called deep CAD. So until now, we talked about the CAD system development, which is basically of the medical imaging, focusing on medical imaging, which is basically a kind of manual intervented shallow machine learning based strategy. But now we will talk about a little bit of deep framework, how these models changes, this paradigm changes from CAD to deep CAD. Now, once we talk about CAD system, deep CAD, the first thing comes out into our mind, the very first in the CNN based CADing. Now, once we talk about the CNN based CAD, we always try to find out the most significant feature, manual extraction of the features. These steps are gone. So once we talk about the CAD system, we are trying to identify the local patterns. We assemble or ensemble those local patterns. We create more larger pattern. In this way, it goes something like that. There'll be input image, feature selection, classification, result. It's a traditional machine learning. Now there should be one input image. You pass through a neural network, it gives you result. You need not to go for segmentation. You need not to go for feature selection, reduction, etc. It will be simply a black box, and you will get the result. So that was the basic motivation of trying to develop the deep learning framework. And CAD system actually, once started deploying on medical imaging on large size data, it gives a very, very high accuracy. It was very promising, rapidly progressing over the time. But ultimately, till now, you can see there are no, I mean, it's not, the CAD system is very much used in common segment. Like say, for example, all doctors are using CADs and patient having trust on CAD. There are a lot of reasons, which I will discuss. But for now, CAD system actually gives you accuracy and the processing time getting faster for the doctors. That is a good positive side. Now, I will try to move into the deep framework now. So until now, I think I was talking about giving a brief idea what are the different challenges of traditional shallow machine learning framework for doing medical imaging. So 2 minutes, I am taking a pause. So if you have any query, please in between you can write. So until I'm audible and the screen is visible, right? Is it?
Yes, sir.
Okay, thank you.
Participants can unmute and ask questions.
Yeah, just 2-3 minutes. I'm just giving a pause.
Okay, sir.
Okay, so let's talk about the learning. So once we talk about the deep learning, this is a very good example by Professor Goodfellow. In 2016, he was trying to, the question was something like that. If there are some triangle and there are some circle, and the question is you have to draw a straight line which will separate these two geometric figure. Now these two geometric shape, by putting a single straight line, it's very hard to segment. I mean, almost impossible, because you are trying to draw one straight line. Now, apparently, it looks to you that it is impossible. But from Cartesian, if you change into a polar segmentation, polar coordinate, like this. So you are changing from xy to r theta. You will see it's easy to draw a straight line, and it will separate these two geometric shape. So only by changing the Cartesian to polar, the problem statement can be resolved. Now again from polar, you back to the Cartesian, and it will be a circle. So once we talk about learning, it's a kind of automatic search process, or you can say it's a better representation of the data. Now you need to come up with a kernel design. You need to come up with an optimal hyperplane design with a different kind of neural network, just to present your data in a better way. That is what deep learning actually is. This is a good interpretation how the deep learning works, and it's different from traditional machine learning. It's a kind of more generic or better optimized hyperparameter setting, you can say, for the better representation of the data. Now, as I mentioned, that you don't need any segmentation. So once, you are dealing with, say for example, CNN, what you are doing, you are simply trying to come up with a kernel design. And here, they say, for example, the image is something like a binary image, 1-0 image, and you have a kernel of size 3x3. Now, what you are doing, you are striding that kernel, 1 stride or 2 stride or multiple stride. And from each stride, there is a patch is getting generated. Now, from every stride, it is getting a patch generation. Now, once these all patches are generated, these are all local pattern of this image. So you are not actually extracting, or you are not extracting the region of interest or doing segmentation. Rather, you are generating the patches. And these patches are so-called local pattern. Now here, the interesting part is, once you are deploying or designing any CNN-based CAD model, you are not manually, or you are not deploying any traditional segmentation. The image creates in own local patches, and those patches can be trainable. So these patch you can train to your machine. So you need not to go for segmentation. You need not to go for any feature selection. Your simple one kernel moving, which is why based on that striding, it creates a local pattern, and each of the patches you can individually go for training mechanism. That is the whole idea. Now, once you're doing this, say for example, your kernel, this is your feature, say one detector. Say so-called this angular are 1, remaining are -1. So once you are doing a kind of operation, which is called the convolve operation, convolution. So what you are doing, you are just simply multiplying 1 into 1 plus 0 into -1 plus 0 into -1, and you are taking the sum of the product. And that gives you 3. You are giving a stride, you are creating say -1, then another stride, you are doing the same operation, sum of product you are taking. And then after that, in this way, you are gradually moving the kernel and doing the convolve operation. Now, once you complete, you will see this whole matrix is nothing but the feature map. So you have a 6x6 matrix image. You are giving a stride. You have a particular feature select detector, and you are simply giving stride and doing a simple mathematical operation, sum of product, which is a convolve operation. This convolution generates a feature map. Now here, interesting part is, if you change the filter, and now these are 1, and you are doing the same operation, repeat the whole process, and giving stride, you will set another set of features. So that means only by changing the kernel, only by changing the filter and doing the same mathematical operation, each time you can create your own feature map. So this is very much exciting thing, because you are actually not doing any segmentation operation. You are not extracting the feature. What you are doing, you are simply moving a particular, passing a kernel. Only by changing the kernel, the feature map is getting generated. And these features you can use for training. So that is the basic, the idea is the main biasness of those selection strategy out of those thousands algorithms are no more. Now here, 6x6 matrix, you are doing the filter operation, and this is giving you a 3. Now here, if you look into this, you will see the whole matrix 6x6, that means 36 pixel values are there. But in this particular 3 generation, this number 3x3, this kernel and this 3x3 matrix is only participating. That means 1, 2, 3 number of pixel, 4, 5, 6 is not participating, 7, 8, 9 is participating, then 10, 11, 12 is not participating, 13, 14, 15 is participating. So it looks like something 1, 2, 3 is contributing for 3, then 7, 8, 9 is contributing, and 13, 14, 15 is contributing. So again, if you go for this only 6x6 for a simple neural network, you need 36 different inputs. But for deep framework, you need only 9 different inputs. So it's not fully connected, it's a shared connection. So that means if you pass this, the number of parameters getting fewer. That is the main notion. So ultimately, from neural network, if you move to deep, the number of parameters getting lesser. So it's a kind of shared weight. Now, if you go for the second operation, you will see for -1 generation, the participation will be 2, 3, 4, 8, 9, 10, and 14, 15, 16. So always the number of parameters is getting lesser. So that is the whole idea for reducing the processing time. So why it is rapid, the main reason of becoming is rapid is the number of fewer parameters. So this way, CAD system is a shared weight, which is the number of parameters getting reduced and it's getting well populated. So these are your patches and you pass through particular neural network. Once you pass through, it creates different output, and these output, you put it into a matrix format. And from that, you are doing max pooling operation and you pass through a neural network. Ultimately, you are getting some result. But remember one thing, Professor Hilton said once, the whole disaster of CNN model lies here. Because max pooling, I will later show you that this is a kind of disaster for CNN. For this, only using max pooling, what is a kind of thing you can see, majority of the cases, CNN not gives the correct result. Why it is so, I'm coming later. But until now, what I try to mean, the image can create its own feature. The features are trainable features, and you pass through a procedure, which is called a max pooling procedure, and ultimately getting your outcome. And this was after 2014 era, once AlexNet introduced, or after certain 2-3 years, there is a ResNet introduced. That many of the model design, they comes, and in medical imaging, there is a dramatic changes. So whole paradigm shift, you can say. People are getting very, very promising result. So this is one interesting website by which you can actually manually change the learning rate, activation function, regularization process, regulation rate, and you can give the classification type also, and it can give you a visual representation how the data is getting, say test loss it is getting or the training loss it is getting. This whole thing can be, you can check. Now, talking about the challenges. So once this deep learning framework comes, the one challenge is the true positive is always good. The patient don't have disease and the test is positive. So it's correct. False cases, the patient don't have disease, but the test is detected as positive. So this is something very, interesting point, because in COVID days, we actually face this problem, the false positive cases. So once we check, it's not only about the accuracy. Later we of the the once that this talk will move, you will see we will always not talk about the accuracy. We should talk about the sensitivity and the specificity, because specificity is a kind of thing, the ability to test correctly identify those patients without having disease. So your CAD system is saying the patient having disease. Doctor is saying the patient having disease. It's good. Your CAD system is saying the patient having disease, but the doctor is saying no, the patient having no disease. Or the doctor is saying you have disease, CAD system is saying it's not disease. Or both of them are saying there is no disease. So the second case where the CAD system incorrectly detects that there is a disease and actually in reality there is no disease, which is the specificity of the system. If the specificity of the system is lower, that means false positive, higher false positive indicates the lower the specificity is. It actually reduces the acceptability of the CAD system, because specificity should not be very high, because if it is a very, should not be, rather you can say that incorrectly detect. So if it is incorrectly detect, higher number of incorrectly detection, that means it's a failure model. So we should not look into only the accuracy, rather we should also check the specificity, the sensitivity, the PPV, the NPV, the ROC curve, the AUC, etc., etc. So this is what the actual thing. Now talking about few other cases, one is the imbalance data. We have disease data, we have non-disease data. The majority of the cases, disease data is very less, but non-data disease is very high. So imbalance is a big issue of medical image. Second is the nature of data. So the patient in Japan, the patient in European country, the patient in North India and South India, the demographics changes, ethnicity changes, food culture changes, smoking pattern changes, so their sleeping pattern changes, everything, the data depends upon all these. So your algorithm might work for North Indian patient, but It might not work for the Japanese patient. Might be the omega intake is different, omega-3 intake is different. Some people used to take a lot of, say, fish. Some people used to take a lot of fast food. So one algorithm, it's not very common that it works for many of the cases. Majority of the cases, it actually observe that it works for a particular demographics of data. Another thing is the quality of the image. As I already mentioned, in medical imaging, the quality of the image matters a lot. And benchmarking data, again, which is actually driven by all the doctors to overcome the challenges and the biases, is a very difficult task. So these are the few of the challenges which the medical imaging having. Now, as of now, what I was trying to talk about, that the actually how the paradigm getting shifted and what is the benefits. So traditional machine learning, what are the obstacles? And if you move to deep framework, what are the advantages? Now we will try to take about, this talk, move towards the deep learning and different major issues and challenges what you will actually face once you do any kind of, say, you can say medical imaging technique, if you try to deploy the segmentation, the deep framework. 1 minute, please. Can we GAN medical images? Yeah, I will come to GAN. No, don't worry. We can use GAN in medical. Yeah, I will come that part. Any other question? Okay, so any machine learning model, it very much depends on, or you can say sensitive to the data which you are feeding. So if you are putting garbage, the output will be automatically garbage. So machine learning model, the first and foremost thing is the data which you are putting to the model, it need to be clean. So even if it is a big data, so-called big data, then also you need to check what type of badness is there in the data. The badness means inconsistent schema, erroneous text, missing data, redundant value, contextual error, garbage value. These are all so-called bad data. Now, if you are feeding garbage value, if you are feeding contextual error, if you are feeding redundant data, missing data, so you will see ultimately it will negatively predicted the model and the overall model will be a failure case. So data cleaning, the very first process, you need to rectify, you need to correct your data properly. So that means there is a nice quotation, all good data are look alike. They are similar. But bad data, they are bad in their own way. Because you don't know which badness is there. The data can be extraneous text, the data can be missing value, so data can be anything. And till now, there is no generic algorithm by which if you pass the data, it will clean the data. No. For all badness, there are different strategy, different algorithm, but there is no common algorithm, one generic algorithm. If you pass the data, it will clean the data. No, such kind of algorithms are still not there. So that's why it's a very interesting task. Now, the second question is, how much data you require for machine learning model? See, as much as possible data you provide your machine learning model, the system will be robust. But remember one thing, as much as clean data. Because if you put more and more biased data, garbage data, automatically the model will be a failure case. So there is no heuristic strategy which actually tells this much of data is required. And medical imaging, majorly, you will see the number of data is very less. And what is the solution to, or how can you get read from there? Now, think about deep learning mechanism. It's a kind of simple memorization technique. You have a lot of data, you are trying to come up with an interpolation, model of interpolation. But what is the difficult part? What is the missing part? The missing part is absence of understanding the relationship in between the data. If you're taking any 2 pixel value, deep learning model failed to identify what is the relationship in between them. So that's why, to overcome this limitation, to understand the underlying relationship in between the data, you need lot of variable data. So it's not like one angle you are taking the Taj Mahal's photo. You need all 360 angles photo and you need to train your system because it failed to understand the variability. To overcome this, you need to cover all aspects of variations. That is very interesting. So it's not about big data. It's not about clean big data. It's all about big, clean, variable data. So as much as possible, you have clean data and variable data, your system will be more robust. So we need to understand we should not chase the data. We should chase always unbiased or variable data and clean data. So deep learning models, whatever the models is, we always try to focus what the objects are, what they are for, how they are typically used. But till now, we fail to understand the underlying relationship, the abstract knowledge, integration of the abstract knowledge. And we are far away from that. So you can see 7 months, say, old infant. He can also identify the abstract rules. From a small level of unlabeled data set, he can solve a problem by 2 minutes. But deep learning models demands, say, trillions of data, sometimes billions and trillions of data, just because it actually fails to identify the underlying relationship, the abstraction of the data. So that's why there are two questions: how much data you need for training and how robust these deep learning mechanisms are. Okay, so think about this one specific problem. If you have a single point, you are trying to fit a curve. Now, if you increase the number of points, you will see the curve fitting will getting better. So it's a kind of better generalization. Now, if you have some points, you are trying to fit a linear regression. Now, if you are increasing the data value, you will see the point estimation will be better. Or if you are increasing the number, the data points, you will see the KNN will give you more better predicted class result. Or if you increase the data point, you will see the splitting of any hierarchical algorithm will be much better. So that means this gives you, for better generalization, better point estimation, better prediction result, better splitting, you need data. So data is important, but that data have to be a clear data and imbalance. I mean, say so-called unbiased data or variable data. But the medical science, what the basic problem is? The basic problem is we have very small size data. So it's not a problem of big size data, rather majority of the cases, it's a kind of small data problem. Because if the data is chronic disease, the number of data is very less. And very less data means it revolves around a high variance value. And the model will getting overfitted. And if there is a very less size data, high chance of outlier, which is dangerous. Say 50 data, one outlier, 50,000 data, one outlier. First case is dangerous. So that's why outlier overfitting and the variance is the biggest problem of small size data. Now, if you think about ImageNet, Professor Lee from Stanford University in 2009, they given a huge data set which is called 14 million data and 80,000 distinct category. So 80,000 distinct category and 14 million hand annotated data, which is so-called ImageNet data. In 2010, during the period of shallow machine learning, the error rate was 28% recognition. And once in 2012, AICTE first time introduced, it suddenly dipped 10%, 16% error rate. And gradually, once ResNet introduced in 2015, the error rate is lesser than the human error. So from 14 million hand annotated data, 80,000 distinct category, your deep learning models such as ResNet, which can correctly identify with an error of 3.6%, which is lesser than the human error rate, to identify or to categorize those data. That is something good. Now the problem is, Professor Hilton in 2012, he come up with an interesting figure. He reported that if there is a 9-layer convolution neural network, only 9 layer, I'm not talking about 80,000 categorization, only 1,000 categorization. Let's talk about 1,000 categorization, not 80,000. How many parameters you required and how many intermediate nodes? You required 60 million parameters and 6.5 lakhs nodes. Now imagine, for 1,000 categorization, you need 60 million parameters which need to be tuned. That's why once we simply add two different neural net, deep learning framework or try to hybridize, we need to rethink how many numbers of parameters we actually need to train, we need to tune, and how many numbers of intermediate nodes are there. So this is something challenging. This is something you can say it's a kind of problem statement, which is a kind of something you can in imaging. It's a huge problem. You need infrastructure, you need that support, you need that data support. So now if you talk about this CNN, the key challenging part. So the objects are sometimes partially occlude. The objects or the color, you can say one particular zone might not be present, information missing. Now, once you try to replicate the object by using any AI, it can replicate the object, and it is very difficult to re-replicate the whole thing. So that's why the key challenge is once the computer vision is dealt with the variance of the data of the real world. So real world data and something to recreate the whole thing is a very challenging task. Now, Professor Hilton has nicely actually pointed out some of the things which I want to mention. One is the ImageNet, which is a 14 million hand annotated data, which is a so-called benchmark data. From that data, we used to go for transfer learning. We used to solve a particular problem on those 14 million data and resolve one problem where the data size is small. Now think this scenario, how ImageNet looks like. ImageNet is something looks like all the chairs are taken from a proper lighting condition, proper shape, proper size, all are so-called good data. But in ImageNet, in 14 million data, there is not a single data which is a so-called bad data. But in reality, chairs are look like something this. So the whole model, even if you are doing transfer learning, based on the ImageNet data, they are so-called bad data. They are variable data, but they are clean data. So your machine learning model, where the frozen knowledge is generating, that frozen knowledge is generating based on the clear data set only. So that is the major problem. So that's why fundamentally you can say it's a flawed data set, because 14 million data, which is a huge data for computer vision, but based on the data, if you are analyzing, the data are all taken into a proper data, proper shape, proper lighting condition, proper angle, proper position. They are so-called, say, ideal lighting condition best data, clean data. So this one, if you try to, see, if you put into CNN, you will see if you are taking one particular angle, if you are taking the trained data, ultimately it will not be identified, it will not be able to capture the information. You need to take all different variations of the data. And this is how actually these CNN models, they don't create the human mind. So that's why to solve this particular problem, the huge data set requirement problem, we need data augmentation technique. So CNN is fundamentally flawed. As I mentioned, Professor Hilton in a conference in AAAI conference, he mentioned, interestingly pointed out, the one is the pooling layer. Now pooling, what we are doing, suppose there is a 3x3 matrix and what we are trying to find out the maximum, and we are throwing remaining 8 pixels. Now we don't know what is the underlying relationship in between those 8 pixels. Some of the pixel might be a good pixel, some of the pixel might be better in future. But without knowing the pixel, we simply discard all those. Only used to keep the maximum or the, say for example, mean pooling. So you are taking the mean value. So this throwing of remaining 8 pixel, which is a kind of, you can say it's a big mistake. And Professor Hilton committed this, that pooling is a kind of biggest mistake or convolutional neural network. And another thing here, if you look into these two images, it seems that these two images are different because eyes are in different places, say nose in different places. But object to object, mouth, 2 eyes, face, oval, and nose, there are 5 different features present here. And you will see output might be same. It will give, CNN will give you the same result. So two images similar, which is not good. So many of the cases, if you are studying the translation, rotation, etc., if you study the max pooling, min pooling, or if you studying this kind of feature, say dislocation kind of thing, you will see CNN not works. Even though we use CNN, comes up with lot of different models, but there are some fundamental issues are there. So to improve the data volume, we need augmentation technique. It's very common. Now, here, so as I mentioned, this kind of model, which there are a lot of, say, 60 million parameters you need to tune. So you need lot of good hardwares. So computationally powered, you can say increased computationally powered, and lot of data you require for this. So data model, the data size of the data and the complexity of the problem statement, it's a kind of increasing day by day. Yes, it is always good to invest time and money to gather more and more data. Now, here, about the healthcare data, as I mentioned, the manual annotation for the doctors is very time consuming. So, or the majority of the data cases, the data size is very small because of different privacy law and patient privacy law, etc., are there. So we are happy with 500 X-ray. We are sometimes happy with 1000 X-ray. So one side 14 million data, one side 1000 data. So gathering is very important, data gathering. But in reality, these are a few of the cases you can take a snap also. These are the databases, which is a very small size data, and people widely use this kind of data for, public data set for research, their abnormality, that the brain data, maybe the breast cancer data, etc. And these numbers are very, you can see 82 samples, 79 samples. And other side, we are talking about 14 million data. So one AICTE you are deploying for 82 samples, one AICTE you are deploying for 14,000 data. So data is important. Now data augmentation technique. Now, once we increase the data size, suppose if you have an original data, you are translating, you are rotating, you are flipping, going for geometric, say, transformation, maybe zoom in, zoom out, maybe shared data, or maybe you are elastic deformation. You can go for contrast stitching, you can go for augmentation, color augmentation, and you are, say, other few techniques like random cropping. You randomly crop the data. You are going for mixing the image, foreground and the background, or changing the variance level. In this way, you can create many images from one particular image. Now think only one thing, this kernel filters. So we change the variance level from 1 pixel, we created, say, another 10 images. Now, these all 10 images are simply generating from the parent image, the first image. So it's a kind of noise propagation or similar kind of information propagation or redundant data. Even though it's a kind of geometric transformation you are doing or something kernel changing you are doing, but ultimately all the data are somehow biased. That means this traditional data augmentation technique, where it's a kind of repeated data trained to your system. Once you are increasing the data size by simple geometric augmentation technique, you are simply putting more and more redundant data to the system. That means what I'm saying is, it's not a clean data. This is so-called bad data because it's a garbage data. It's a redundant data. So even though the data size is getting 10 folds or 20 folds by these kind of techniques, but ultimately all these are somehow biased. So that's why you need some strategy where you can, actually come out from this biasness. One solution is GAN, definitely, generative adversarial network, where image to image translation, say winter image can be changed into summer, summer can be autumn, etc., which is a kind of robust but computationally intensive mechanism. You need a cheaper solution. That solution is called the neural trial transfer. So you change the texture, ambience, appearance of an image, and you can create many images. So this is one, say, true image, one synthetic generated medical image. And it's very difficult to actually identify which one is the synthetic data. And in this way, you can upfold your data size. You can go for augmentation. And neural trial transfer, which simply, as I said, you change the texture, the style, the appearance, etc. This is study Stanford 1, where you change based on the theme you change that, even you can recreate the image. This is one example, like Kanagawa wave. And if this is an MR image, and that MR image you can put into some particular template and you change that image. This is called the neural trial transfer. And you can create many images. And in the GAN, as we know, there are two different modules. One is called the generator, one is called the discriminator. So generator creates a fake data, and which looks like a training data set. So if you have a normal and uniform distribution noise, Z is a noise, you are passing the Z through a deep framework, which is called the generator G, and that gives a G of Z, which is X. X is a kind of fake data, and you are passing the fake data to the discriminator. And discriminator, what it's trying to do, the generator is trying to fool the discriminator, and discriminator is trying to identify the data is real data or it's a fake data. So it's always gives with a probability that it's a good data, it's a correct data, real data, or it's a fake data. So once the latent space, the noise is passing through here, G of Z, that is a X, it passed to the generator. There is a pool of real sample data, and it is getting checked by the discriminator. The discriminator is trying to, with a probability, it's trying to identify it's a correct data or it's a not incorrect data, fake data or real data, and the process will continue. Here, you can see there are, these are the theta 1, theta 2 are basically the parameters. So Z is Z of Z, theta 1, which is actually the desired outcome fake data X. X is passing to the discriminator, D of X, with a probability in between 0 to 1. And what is the objective? The objective is twofold. One is the maximizing, one is the minimizing. What you are trying to maximize? You are trying to maximize the probability that the real data set X needs to be classified as the real data. And what you are trying to minimize? That the fake data should not be classified as real data. So it's a kind of max-min problem. You are trying to maximize the function of D of X and minimizing the D of ZZ. ZZ means the fake data X. So D of X, you are trying to minimize. That is a whole idea. So it's a max-min problem. And what it try to do, there is always, it's a kind of classification problem. So there is a loss function. So the error function of the neural network, it's a max-minimize. So that is D of ZZ. We always the logarithmic one. Why it is logarithmic? Because in the logarithmic function, if it is correctly identified, it's okay. But if it is incorrectly identified, the penalty will be very high. So log loss is a kind of highly penalty gives to the classifier. So that the tendency of doing mistake of the classifier will be less. So that's why we use the log loss function. Now you will see after several steps, the generator creates more and more realistic image, and discriminator failed to identify this is a fake image, and there will be a tussle, and it's generate more and more synthetic real data. After a certain point of time, based on the, this Nash equation, max-min game formula, you will see it will try to optimize the loss function. And one time, after a certain iteration, you will see the generator failed to create more realistic data, and the discriminator might not be able to identify it's a fake data. So it will pass the discriminator, and in this way, you will create the synthetic, more realistic data. So that is the whole idea how the generative model actually works. So this is can be the solution of generation of synthetic data. And the second data can be the transfer learning model. So transfer learning model, what actually, if you have a lot of data and you are trying to solve a problem where the data size is very less, as I said, 42 samples or 82 samples. Now you have 14 million data. So you actually try to solve the problem on the large set data. You pass the knowledge as a frozen knowledge or pretend model knowledge and try to solve a problem where the data size is small. So the idea is you are trying to solve a problem called B by solving a problem A where the data size is large, and you actually pass the knowledge to B as a frozen knowledge or pretend knowledge, which is actually, you can say, lesser computation resources you required rather than GAN. But in reality, what happened, as I mentioned in transfer learning model also, all the data, if it is a clean data, so-called clean data, ultimately the result you will get somehow biased, because ImageNet data, as I mentioned, all are good data. So here the good data and bad data should be there. so that the model will be much more robust. So if you have this kind of data set for all from the simple domain, say same domain, say this is a pathological, say histological data, all are histological data, or if the data set is different, then might be sometime you need to tune. So the last layer, you need to actually tune the test images to increase the robustness. So transfer learning model intermediate nodes sometimes need to require some tuning. And there can be one-shot learning also. Like in deep learning model, the model can look any example from a large test data set and during the training period, and it can identify. And in one-shot or zero-shot or k-shot learning, it's a different area where people actually used, especially for the face recognition area. But if the two pictures having the same dog or same car, it failed to identify. If the person wearing hat, scarf, or maybe the glasses, it's failed to identify. There is a one example in 2015, how one-shot learning unfolds the brain. It's a very interesting paper where people actually tried to first incorporate how the one-shot learning can be deployed into medical imaging. These are how the synthetic data can be generated. These are the ways. One can be the transfer learning, one can be the GAN, maybe one solution can be the one-shot learning. But apart from these, people are still working in this area where they're creating more and more synthetic data, because augmentation traditional technique having a lot of fundamental challenges. Okay, so in between 2-3 more questions, please. Then I will again. Okay. Now coming to the issues, the challenges. One is, if you, instead of segmenting the whole image, which is called the semantic segmentation, which is classified by pixel, not as a whole image. So if you train your model patch-based, if you train your system patch-based training, is very crucial, because sometimes it's instead of whole image training, if you go for patch-based training, you will get more better result. So it's a kind of batch selection or the random patch selection. So it's a kind of sampling technique. But if the sampling are overlapping, you will get high accuracy, because overlapping sample always gives you high accuracy, but computationally intensive. So we need to properly select the sample for a faster convergence and balance the classes. So performance improvement can be carried out by non-overlapping patches, sizing of mini patches sizes. So this is one example. Instead of whole image, you segment it, maybe semantic segmentation you are avoiding. You are trying to come up with some small patches, and you are doing the training patch-based training. So that can be actually, it can help to augment the data also as a patch-wise augmentation, and it can go for increasing the data volume also. So you will get a better result. One. Second is weekly supervised learning strategy. So weekly supervised learning is a very interesting strategy. If you have annotated data, you supervised learning, go for it. It's too expensive. If you have less number of annotated data, you can go for less accurate semi-supervised learning. If you have small size annotated data, you can go for the transfer learning also, which may be accurate. If you have no annotated data, you go for unsupervised learning. But in between, there is less or more in between weekly supervised learning. Suppose, say for example, the doctors are not available, so the engineers are doing the benchmark data for you. They are hand tracing the tumor. So it's very common that they will do mistake. So that's why it's a cheaper solution to take the benchmark from non-expert. So you don't have correct annotation, but you have some annotation. So that's why this is called a weekly supervised learning strategy, where you have some delta error. But considering the delta error, you can improve the overall performance. So it's a kind of heuristic identification of the pattern, maybe the unsupervised strategy also, which helps to improve the model accuracy in between supervised and unsupervised, considering some certain number of errors and biasness, which is recurring bias. That is a weekly supervised learning strategy. Now, sparse annotation, the whole image might not be actually useful for you. So you try to identify the region of interest and you put a flag 1, the remaining will be 0. So just like in sparse matrix, the number of non-zero element will be less, the 0 element will be more. Here also, it's a kind of on-off switching, and then you train your system. So you'll see sparse annotation will improve the training time and improve sometimes the accuracy also. It's a kind of patch-based model design, but again, it's a simple strategy just to make it on-off by 0 and 1. So label pixel, unlabel pixel. Now, effective negative set is very important. You have a lot of, say, data and say disease data, very less non-disease data. So that is very problematic. So what you need always some balanced kind of data. Otherwise, you will see that discriminator will not able to properly discriminate two data set. So if you don't have any negative data set, you should incorporate some negative data set into your system. So that is with the effective negative data set, so that the classifier will correctly discriminate these two. An imbalance problem, as I mentioned, is the biggest problem. You need to balance your data set. Otherwise, you will see it's sometimes not giving you a proper result. So patch-based modeling, again, can be a proper strategy for balancing the data set. And there are a few other challenges like overfitting cases. As we know, the model getting learned parameter to specify the training data. So irrelevant in the other data which actually occurs during the overfitting cases. If the data size is very small, you will get better accuracy. But ultimately, the validation matrix, if you look into the validation matrix, you will see it's improving. But stop improving after a certain number of epochs. Then it is getting decreasing. So you need to always check that training and validation both matrix. Is it both are improving, or one is improving, one is not improving, something like that, so that you can identify the overfitting cases. So once you have overfitting cases, the solution is you have to lower the capacity of memorization technique. You have to lessen the memorization technique. So to reduce the memorization technique, there are some strategy like regularization strategy, L1 regularization, L2 regularization, dropout cases, etc. This can be a solution for handling the overfitting cases. And learning rate, this session might be, I will take another 10-12 minutes. Then next session, I will manage this thing. In the learning rate, once you talk about the learning rate, one of the learning rate is basically to configure the hyperparameter. We know there are a lot of hyperparameters associated with any network framework. Like say, for example, as I mentioned, 6.5 intermediate node, 60 million parameters. So one of the most, important hyperparameters we need to configure is called the learning rate. Now, what happens? Learning rate, the error estimation amount, which is a kind of weightage, you can say, which gives, that needs to be optimized also. There are different strategy like ADA delta, by which you can optimize. But learning rate is the most crucial factors which need to be properly optimized so that the neural network, the model will actually give you a proper desired outcome. So this is another important point. Then there are two issues. One is called the vanishing gradient. One is called the exploding gradient. So if the input and the output, you will see it's approaching to the 0 eventually. So the weight of the initial or the lower layer is nearly unchanged. So it's a kind of gradient descent problem. So it's a vanishing and the exploding. The opposite is the exploding problem. One is the getting larger and larger, the input and output. So these are the two typical problems which you might face. One is a vanishing problem, one is a exploding problem. The solution can be a batch normalization. It's a kind of gradient clipping is there, or you sometimes uses the ReLU also. And deconvolution is a strategy which actually helps to come out from these particular problems, which is called the vanishing gradient problem or the exploding problem. And one pixel is a very interesting paper in 2019, comes in TEC, where the authors reported 1 pixel can make the difference. So if you remove 1 pixel, a dog can be an automobile or a dog can be a cat. So deep learning systems are quite good at many large fraction of cases, but it can be easily fooled. The robust system requires more and more study. You may go through this paper. This is called 1 pixel attack. How can be a deep learning framework getting fooled? So this is one generic diagram. If you are dealing with ultrasound analysis, the methodological task, what you can do means localization, detection, classification, segmentation, registration, etc. In different modalities, it's biometric measurement, etc., which I will discuss later. And there are also the modality, like if you're talking about which particular application area you are dealing. So it can be breast cancer, liver cancer, maybe the heart disease, brain, carotid, thyroid, etc. Majority of the cases, how the research carried out, number of papers based on that. So you can see for the detection is the majority, then comes the classification, then comes the segmentation. And in the year-wise also, the majority of the cases, I started from that detection. So this is detection area where the majority of the paper comes out. These are few of the medical competitions which are open data set, you can say, and every year many people used to participate these open data set challenges. And these are some medical data set where the data size is huge. As I mentioned, few of the data set where the data size was very less, but these are for public data set, you can say, where the data size is a huge data, where lot of patients data you can actually gather from this public data set. And lastly, 2-3 more slides. Once we talk about the explainable AI, so we need more and more robust system, transparent system, interpretable system. And for that, responsible AI plays a significant role. Initially, once we check the performance, you will see the performance is very lesser in the rule-based model. Then gradually we move to, say, Markov models. And from Bayesian Markov models, we move to the statistical model. Then we move to ensemble model, say random forest or all. Then we move to deep learning. So gradually the performance improves and the explainability of the model is getting lesser and lesser because linear models are very much explainable. But once we talk about deep learning, it's very less explainable. So that's why many people actually, this is a very interesting work where the people talk about why should I trust your result? So if you are reporting something very interesting outcome, maybe 99% accuracy, why should I trust your result? So for that, explainable AI plays a significant role. And nowadays, everyone talks about that lime and shape, that which part of a particular image is significant, which for the local interpretability or the global interpretability point of view. And this is not my concern. My major concern is once we talk about this explainability model, the last point is very important. Explainable model always deals with AI model interpretability, but never talks about the training data set. The data which we are providing might be taken from different geographical area. And once we are trying to explain one model, the transferability or interpretability, we always talk about the model transferability. We always talk about the reliability of the model. We never talk about the training data. But data quality is a big factor for any machine learning model. So we should not focus on the models. Rather, we should also focus about the data. So this need to be actually studied more. We should not talk about XAI designing for the data model. We should also talk about the training data set. And lastly, in medical science, machine learning is always good, but human in a loop machine learning is important because human intervention should be there. And another thing is once we create more and more synthetic data, we should be think about the realistic point of view, how real the real enough. Because my fake data should not be so fake that it should pass a real scenario. So there should be one cap where we need to think and rethink that we should stop here. We should not care more and more synthetic data. And lastly, the very important point is machine unlearning. We always talk about machine learning. We should think about machine unlearning. What is unlearning? Say, for example, today I provide a data for machine learning model. After 10 years, I realize that I want to revoke my data. I want to get back my data. I not want to share my data, which is very common because of the privacy issue. Now, if some people are not interested to share their data anymore, what will happen? After a certain point of time, the model need to be retrained. But retraining is always a costly process. So you can't retrain model always. So you need to come up with some algorithm. Even if you revoke the data, Even if you remove the data, omit the data, delete the data, the machine learning model will give you exact result, almost same result. So that's why this strategy is called machine learning, which is very, very crucial for medical imaging, because medical data, many people sometimes they revoke their data of different data privacy policy. So I think I need to conclude. It's almost 1 hour, 30 minutes, 35 minutes. So if anybody having question, please, feel free to ask then.
Good evening, sir.
Good evening, madam.
Sir, my question was, can we rely on GAN images for detection of diseases? This was the first question.
Yeah.
And second question was that you said optimization technique, right?
Yeah.
So we change the weight.
Hmm.
So if we are not getting the data, then what exactly happens when it comes to the fully connected and then you are not getting the proper result, then it come back, means back propagation. So what exactly happens by changing the weight and
Yeah, madam, got your point.
Yeah.
Madam, this second line is very important. This how real enough
Yeah.
means where to stop. See, people are all chasing those synthetic data generation. Means everyone is creating more and more, say, generative framework, something like that, to create more and more realistic data. And this is actually required. Say for machine learning, we need lot of data. But the diagnostic value of the data is very important. As I mentioned that some data, definitely if it is a real data, have some diagnostic value. See, all these images, all these medical images having their own different types of noise. Say, for example, some image having speckle noise, some images having different types of noise is there. So once we create those synthetic images, those real life scenario, those diagnostic measure might not be there. So whenever we are dealing with synthetic data, it's always good up to a certain level. But once we are validating in real life scenario, we need to pass through a particular explainable model that even if the data is good, but this is synthetic data, we need to stop and rethink that model is correctly giving result or not. It's a trustable result or not. That's why one point I mentioned that once there is an XAI, XAI model always talks about the result is good, the model is working fine, how it is working, but it never talks about the data which deals with.
Yes.
So that means XAI model also should focus on the data part, because as the generative model giving more and more realistic data, XAI is interpreting the model, but never interpreting from the data point of view.
Yes.
So that is what actually I mentioned the last one, that explain the behavior of AI model, not the behavior of the training data set. That is the one of the major limitation of XAI. So there is it's a high time we need to rethink that how much data we will create and where to stop generating synthetic data, and to explain the model along with the data which is intervening those CAD system. This is first. And
Yes.
second is the weight. See, weight initialization is a kind of thing which we used to say, if you are lucky, then it's good. Your starting point will be good. But initial weight setting is it's a kind of, you can say it's a trial and error kind of mechanism. If you're correctly identify, it converts very fast. If it is not correctly tuned, it will convert later. So there is no such kind of, I don't know any kind of such strategy which actually gives you an initial value to the weight so that the convergence will be much more faster. But it's a very interesting, open, challenging problem. Means how to identify the value so that it can easily, you can say the convergence will be very fast. But it's an optimization problem, typical optimization problem.
Yes, sir. Thank you. Thank you so much.
Thank you, ma'am. Any other question, please? Okay, I think no more question. I already bored a lot. It's a 1 hour 40 minutes.
Thank you, sir,
Yeah,
for
ma'am.
your valuable inputs on medical imaging. Sir, our next session will be start within 5 minutes. So we have a break of 5 minutes. And after that, we can start the next session.
Madam, not 5 minutes. Give at least 15 minutes. So,
Okay, sir. Okay,
so I
sir.
think it's 7:48. So we'll start at 8.
Okay, sir. Thank you. So we have the break of 15 minutes. All participants are requested to join at 8 p.m. Thank you, sir.
Thank you.